Hello everyone, let me introduce myself. My name is Honesto Pardede. I'm a mechanical engineering student from Teknik Fakultas Udayana University. I want to represent about metallurgy, discovering metals, and a historical overview. We got a referency from Metallurgy for the non-metallurgists, edited by Arthur C. Reardon. We got to the content. We got 4.1 the native metals, 4.2 the Bronze Age, 4.3 the making metals extractive practices, 4.4 iron, 4.5 discovery of modern metals, and 4.6 refining of metals. Let's jump to the 4.1 the native metals. Native metals. Most metals naturally occur as mineral or compounds. The metal atoms have reacted with other metals or with non-metallic atoms. One of the primary tasks of the metallurgy is to extract the metal from the compound. The few metals that are found in the unreacted state are termed native metals. Through the use of native metals, the science of metallurgy was born. As we can see in table 4.1, the chronological list of developments in the use of materials. You can see in my slide the points found in North America, but most of the copper was used for ornaments. Other civilizations, such as those in Egypt and the Middle East, note that copper hardened and strength significantly when hammered. Although the term nanotechnology was clearly not used, these ancient metallurgists were hammering to control the number and configuration of the nanocrystalline elements of the structure of copper. The hardened copper became useful as a tool, and thus the Copper Age was born. Knife could be fabricated for agricultural uses and for cutting the flesh of fish and game. However, such knives were generally useless for the penetration of hides or the cutting of bones. Thus, although copper knives serve a purpose, they lack the strength of serve as effective weapons. The discovery that copper could be obtained by heating covellite, malachite, and other bright blue stones or minerals was made between 4000 and 3000 BC. These were primarily copper sulfate ores. An ore is a natural mineral that can be mined and treated for the extraction of any of its components, metallic or otherwise. The metallic component of copper sulfate mineral is copper sulfur, is one of the non-metallic elements. Extraction of copper from copper sulfate ores provide ancient men with another source of copper. Once extraction techniques were developed, the use of native metal was not restricted. Now we got to the next slide, the 4.2, the Bronze Age. The Bronze Age began when it was discovered that mixture of two metals or alloys were stronger than either of the metal taken individually. This discovery was probably made about the same time that extractive metallurgy was discovered. The discovery that thin alloy addition strengthened copper was the crux of the Bronze Age. A chemical analysis of a typical bronze alloy from the ancient Middle East shows that the alloy contained approximately 87% copper, 10 to 11 tin, and small amounts or less than 1% of iron, nickel, lead, arsenic, and antimony. It is rather startling to realize that approximately 4,000 to 5,000 years passed between the advent of the Bronze Age and the development of sterling silver, a more modern application of strengthening effect of alloy in addition. Sterling discovered that the strength of silver could be improved greatly by the addition of small amounts of copper. This small addition, approximately 7.5%, did not affect the appearance but significantly improved the serviceability of silver vessels, jewelry, and utensils. As we can see in figure 4.1, a bronze koi-handled vessel on a rectangular plane, cast in China in the 7th century BC. Now we got to the next slide, the making metals extractive practices. Most metallic elements occur naturally as minerals or ores, which are compounds that result from a reaction between metallic and non-metallic atoms. Common native and minerals occurrence of matter are listed in table 4.2. Most copper, zinc, and lead ores are sulfides, while iron and aluminum are generally found in oxide ores. Although modern extraction processes are complex, the smelting process can be very simple. For example, early North American settlers smelted lead sulfate or galena to produce lead ball for bullets used by most colonial woodsmen. Galena is the most common lead ore, and the lead was extracted by building a fire inside a hollow tree stump and roasting the galena ore on the fire. This process resulted in the lead sulfide or galena reacting with oxygen in the air to form molten lead and sulfur dioxide. Although extraction of lead from galena had been widely practiced for many years, it was not widely recognized until relatively recent times that silver is associated with lead extraction from galena. Lead sulfide ore generally contains appreciable quantities of silver, and because of the potential for silver recovery, lead smelting is currently practiced under very controlled conditions. We got to next slide. The iron. The early name for iron means stone from heaven. In several languages, this name probably resulted because the first iron used by ancient men was literally from heaven. Meteorites weighing from a few ounces to tens of tons. As we can see in figure 4.2, lead blast furnace, open top type. This furnace is termed a blast furnace because of the air blast used to smelt the ore or coke mixture. Have been falling on the earth since its beginning. The meteorites frequently contain large quantities of metallic iron, and the first iron used by ancient men was from these stones from heaven. The first iron extracted from the naturally occurring iron oxide deposits could have resulted from primitive men building a wood or a charcoal fire at base of some one-step cliff. If the cliff outcropping happened to be rich in iron oxide, after days or even months of use, the fire cooled and the ashes contained a small amount of iron sponge. This sponge was the iron that remained after the oxygen had been removed. The iron had not been melted during its production. Like the iron in the stones from heaven, the sponge could be hammered into shapes and was relatively strong. Spears, arrow tips, daggers, and other tools and weapons could be fabricated. The first iron to be developed was wrought iron. Wrought iron can readily be forged to shape. In fact, the term wrought means to shape by hammering or beating. Wrought iron is very ductile for forging because it contains very little carbons. It less than 0.05%. Carbon is an interstitial impurity that strengthens the iron lattice. In fact, iron alloys that contain between approximately 0.1 and 2.0% have a special name. It's called steels. Iron smelting, as we can see in figure 4.3. As with the reduction of copper sulfate ores, the first reduction of iron oxide was probably accidental. The temperature in blast furnace are approximately is 150 to 200 Celsius, and the Fahrenheit we can count to 300 to 400. Because of the rising stream of hot carbon monoxide that results from combustion of the coke at this temperature, the carbon monoxide begins to react with the iron ore to free some of the iron. At the same time, some of the carbon monoxide is cooled by the charge and form carbon dioxide and free carbon. This free carbon is soot that darkened the skies over iron production cities from the 6th through the mid-20th century. Removal of this soot from the rising blast is difficult and represent an ever-present problem common to the production of the metal from their ores. As we can see in figure 4.4, the schematic of a blast furnace. Steel, which are iron containing between approximately 0.1 and 2% Celsius, combine the toughness of wrought iron to the strength of pig iron. Steels can be made from wrought iron by heating the iron for a long period of time in a red-hot charcoal fire. The hot iron absorbs carbon from the charcoal so that carbon atoms diffuse into the iron layers. The result is an iron-carbon solid solution alloy that we know as steel. The increase in carbon also provides other advantage in the strengthening of steel when it is quenched from elevated temperatures. Okay, that's it. We got to the next slide. 4.5, the discovery of modern metals. The discovery of modern metals. The use of a Latin suffix in the naming of metals such as beryllium is typical of the suffix on all metal discovered or isolated after 1800s. Many of these metals have tremendous commercial importance, primarily because of their use as alloying elements. Alloying elements are generally added to improve the mechanical, electrical, or chemical properties of other metals in a fashion similar to addition of tin to copper to improve strength. Some of their commercial use of several of the metals are described subsequently. The point one is beryllium or Be. Is added to copper to improve its strength. The mechanism or process by which beryllium increases the strength of copper is very different than the strengthening that results by tin or zinc addition to copper. Zinc addition to copper produces brasses. The copper beryllium alloys contain only a small amount of beryllium, approximately only 2%, but can be processed or heat treated to be much stronger than any low tin brass or copper zinc alloy. These very high strength copper alloys are used for the production of springs in the electrical industry and make non-sparking tools for use in potentially explosive atmospheres. And then cadmium. Cadmium was discovered in 1870 and is primarily found in zinc ores. Cadmium coatings or plating were used to protect nuts, bolts, and other components made of high-strength steel or other relatively corrosion-prone metals. The cadmium plating acts much like some paints and limits the access of environment to the protected component. Many of the components in commercial aircraft are quite plated. Cadmium is also an addition for some dental alloys because it increases the strength of the filling. The increase in strength improves the wear resistance of the filling and prolongs its life expectancy. However, cadmium has adverse environmental consequences, and efforts to replace cadmium with an equally effective coating are ongoing. Next we got chromium. Chromium was discovered in 1798 and is used mainly as an alloy addition in steel production. Chromium improved the resistance of steel to oxidation and corrosion and is essential ingredient in stainless steels. Corrosion would severely limit the utility of the steel if chromium was not added. If the chromium was not added, it will increase the corrosion rate. Stainless steels contain up to 30% Cr, and although the primary function of chromium addition is to improve the corrosion or chemical behavior, chromium in small quantities improve the strength of alloy steels. Next we got molybdenum. Was discovered in 1781 and is primarily used as an alloy addition to steels. However, molybdenum melts at 20,620 Celsius for iron. This difference in melting temperature complicates combining the two metals into an alloy. Because of this high melting point, molybdenum alloy with tungsten and rhenium is called a refractory metal. The term refractory generally applies to a wide range of ceramic materials and other high melting points compound. The refractory metals are not compounds but have relatively high melting points. Because of its high melting temperature, molybdenum is used in the manufacture of high temperature heating elements and furnace trays. Work to develop molybdenum alloys for gas turbine application is one of many studies designed to obtain metals and alloy for every high temperature application. Next we got tungsten. Tungsten was first refined from ore in 1783 and was originally called wolframium. Tungsten was first used as the filament for the incandescent light bulb, and this use accounts for 50 to 20% of all tungsten use. The major use of tungsten today is in the form of tungsten carbide, which is a very hard, wear-resistant materials. Carbide tips, drills, and machine tools insert account for 65 to 70% of all tungsten use and are found throughout the home and industry. It is interesting to note that tungsten, which is very brittle, high-strength material at room temperature, can be fabricated into the fine wires required for light bulbs. Next we got vanadium. Is among the hardest of all relatively pure metals. It was discovered in 1830 and it is actually more abundant than copper, nickel, or zinc, but is very difficult to purify. Vanadium is primarily used as an alloy addition to steel from the manufacture of woodworking and metalworking tools. Then magnesium. Magnesium is the lightest of the widely used structural metals. Magnesium is more than 1/3 lighter than aluminum, having a density of 1.7 gram per centimeter compared to the other density of aluminum. Because of its low density, magnesium has been used in aircraft frames like airplanes, helicopters, etc. It is also an important alloy in elements and aluminum. Magnesium, however, can ignite very readily when finally divided and is actually used in flares and other pyrotechnic devices. Like many other metals, magnesium is rarely used for structure in its pure form, but becomes a useful structural material when alloyed with aluminum, manganese, or zinc. Titanium was discovered about 1719, but because of the difficulty of freeing titanium from oxygen and nitrogen, it was not readily available as a structural material until the 1940s. Titanium is difficult to process and to shape, but has both a high strength and low density. This gives titanium the desirable property of having a high strength to weight ratio. It is the strength to weight ratio that makes titanium alloys desirable for aircraft and spacecraft application. Because of its natural corrosion resistance, titanium is also used in chemical process industry and for orthopedic implants. Now we got iridium, rhodium, palladium, and platinum. These things are, along with gold, termed the precious metals. They are all very dense and very corrosion resistant. However, the term precious metal comes from the fact that all these metals are expensive. Because of this expense, the precious metals are used as catalysts and for applications that typically call for small quantities of materials. Pen points, electrical connector, dentistry, and pivot points in fine balances are examples of uses of precious metals. Platinum, iridium alloys are very resistant to food acid and are useful in dental restoration. For the final, we got aluminum. Aluminum is the third most abundant element on the face of the earth. It's a member of the family of metals that includes gallium, indium, and thallium. Aluminum was not discovered until 1825. Very pure aluminum like copper, gold, and silver is too soft to be of much value as a structural material. However, commercially pure aluminum and aluminum alloyed with copper, silicon, magnesium, zinc, and other metals have many industrial applications and are second to steel in volume of material produced commercially. Now, for the next slide, we got refining of metals. Refining of metals refers to process that purify extracted metal. Refining of metal, like the extraction of metal from ores, includes many ancient practices and more modern advances. For example, gold always occurs in a metallic state, and it can be extracted from minerals by relatively simple means. That is, penning and sluicing for gold effectively separates the gold from minerals such as sand or gravel, because the density of gold is much higher than that of mineral. For example, we got quartz in sand has a density of approximately 3.2 gram per centimeter. Penning and sluicing with water washes away like sediments from gold nuggets or flakes. However, the remaining gold flakes or nuggets are not necessarily pure. Further purification steps may be needed. Gold refining is the relatively simple process of heating the gold to a very elevated temperature. At this high temperature, most of the impurities of the gold react with oxygen in the air to form metal oxide. Some of the oxides formed by such reaction are gaseous and therefore carried away by the surrounding air. Other oxides are not gaseous, but the reaction to form these oxides produce relatively low density compounds that float on molten gold as a slag or dross. The slag floats on gold is much the same manner as wood floats on water. Therefore, gold can be refined by simply scraping the floating debris from the pool of a molten metal. This technique is refining gold was known by the period 2000 to 1000 BC. As we can see in figure 4.7, the micrograph of non-metallic inclusion in typical commercially pure aluminum, originally magnificent. In the figure A, we got an annealed structure, and for the B figure, we got a cold work structure. And the second figure, in figure 4.8, we got a titanium heat exchanger using several grades of commercially pure titanium. Very high purity metals are often to solve for any type of structural application. For example, gold that is 99.999% pure is non-practical, even for use as chains or pins in jewelry. However, some other material specifications require exceptional refining technique, silicons, as well as germanium and other metals used in the semiconductor industry must be produced at controlled purity levels equal to and exceeding less than 1 impurity atom for every million atom of pure element. Such high purity is needed when strength is less important than other properties such as electrical conductivity. In the transistor industry, it is now common to be concerned about both alloy addition, the elements added on purpose, and impurity levels, the element whose removal is desirable. At concentration level of 1 part per billion, that concentration level is 0.0000001%. We got to the next slide. I think that's all I've got. Thank you so much.